So now I want to talk about the complex numbers as a field. Okay, and what I mean by a field is I mean the object that you study in abstract algebra called fields. And again, if you've not had any abstract algebra, that's totally fine. I think this there'll be just a tiny bit of algebra throughout, but I'll be able to kind of explain what I mean without you having to go through all of algebra. So when I say that the complex numbers is a field, what I mean is that it's a set with two properties of multiplication and addition, and it has all of the following properties. So it has commutativity. So let me use Z1 and Z2. So if I were to add two real numbers, the order doesn't matter. If we were to multiply two real numbers, the order doesn't matter. So these are commutative properties. Okay. If I were to add three complex numbers together, or if I were to multiply three complex numbers together, the order doesn't matter. So it doesn't matter if I group the last two first or the first two first. It's going to be the same when I do this with the products as well. So these are called associative properties. As far as mixing addition and multiplication, there's a distributive property. So if you were to have Z1 times Z2 plus Z3, this works out to exactly what you would think. Z1, Z2 plus Z1, Z3. So that's called the distributive property. There's also identities. So if you were to take the number 0, and by 0 I mean 0 plus 0i. So 0 is a complex number. This is the additive identity. Okay, so this is the additive identity, meaning that z plus 0 is z for all values z. And likewise, the complex number or real number 1, which we're thinking of as 1 plus 0i. So really when I say complex, I mean just because we're thinking of this in terms of complex numbers, so it has a real and an imaginary part, even if the imaginary part is 0. Anyways, the number 1 is the multiplicative identity, meaning that you can multiply any complex number by 1, and you get back that complex number. Again, that's for all complex numbers z. So there's the existence of additive and multiplicative identities. There's additive and multiplicative inverses. So if z is a complex number, then there exists, this is going to be silly, but there exists minus z. So minus z is also a complex number, so that when you add these numbers together, you get the additive identity. Likewise, if z is a complex number that's not 0, then there exists a multiplicative inverse. So then there exists a complex number, which I'll call z inverse, where z times z inverse is equal to the multiplicative identity, 1. Okay, and this is one of the properties really that sets a field apart. And so one of the features of fields is this one, and that's a big one, is that every non-zero value has a multiplicative inverse. So this is true of rational numbers, this is true of real numbers, this is true of complex numbers. And this is one of the defining features of a field. And it turns out that these fields that we're talking about, so the complex numbers in particular, and the reals and the rationals, are exactly the sets over which you can study vector spaces. So you can always talk about vector spaces over fields, where fields are these sets, namely, usually when in linear algebra, you start with the real numbers, but you could easily go with the complex numbers as well, okay, or even the rationals. The integers are not a field because there's no multiplicative inverses. So for example, the integer 2 doesn't have a multiplicative inverse that's also an integer. The multiplicative inverse of 2 is 1/2, and you're thinking of that in terms of rational numbers now. So that's why the integers themselves are not a field. If you want to do division, I think that this is worth talking about. What does it mean to divide two complex numbers? If you were to take z is, say, a plus ib, and w is c plus id, then z over w, let me just write this a little bit better. There's a little trick here. So then z over w, which would be a plus ib over c plus id. What you do is you always want to divide by a real number. And so it turns out that if you multiply the top and bottom by some tricky number here, in this case, it's going to be what's called the complex conjugate of the denominator. In other words, take the complex number and change the sign. We'll talk about complex conjugates in some detail as we go along. But it turns out what you do is in the denominator, you're going to end up with, think about how the multiplication rule works. You're going to end up with c squared minus I squared d squared. And then because they have opposite signs, the other terms cancel. And then in the numerator, you're going to end up with, let's see, ac minus I squared bd plus I times AD plus BC. Now, the point of this is not to memorize anything. The point of this is that if you multiply by the complex conjugate, what ends up happening is that the minus I squared, well, I squared is minus 1, so minus I squared is plus 1. And what that does for us is in the denominator, it makes the quantity real. And so now what you're doing is you're taking a real number and you're dividing it by, you're taking a complex number and dividing by a real number. And you can break this up further if you want and think about the real part of the numerator divided by the denominator and the imaginary part of the numerator divided by the denominator. And now that makes perfect sense. And you can write this as, if you'd like, AC plus BD over your denominator, c squared plus d squared, plus I times the other quantity, AD plus BC over c squared plus d squared. Okay, so in general, that's how multiplication works. That's how complex division works, is that you want to multiply the top and bottom by the complex conjugate of the denominator so that you're really just changing this to a problem about dividing by real numbers. Okay, and so that's the idea. We'll do some examples of that as we go along. One proposition I want to talk about is that there's always going to be square roots. Okay, so I'll mention this and then we'll prove this in the next video. Okay, so I'll call this a proposition. For all complex numbers z, there exists a value w in the complex numbers so that w is the square root of z. What I mean by that is that w is the thing that you have to square to get z. Square roots are actually a little bit subtle and a little bit tricky, and we'll talk about them later in this chapter. But the point here is that every complex number has a square root in this sense. There's always a number that you can square to get z. Okay, and so we'll prove that in the next video.